Different non-vertical lines have different slopes or y-intercepts or both. They're graphs of different linear functions. Functions that their graphs form a straight line. For two such lines, you can think of one as a transformation of the other. Linear functions form a family of functions. Each linear function is a transformation of the function y equals x. So that y equals x is what's called the parent linear functions. All other linear functions originate from that parent function y equals x. Just like you originate from your parents, all linear functions originate from y equals x. The function y equals x, once again, is called the parent linear function. A parent function is the simplest form in a set of functions that form a family. Each function in the family is a transformation of the parent function. So for linear functions, the parent function is y equals x. When we get into quadratics, the parent function is y equals x squared. And for absolute value, the parent function would be y equals the absolute value of x. One type of transformation is what's called a translation. A translation shifts the graph of the parent function horizontally, left and right, vertically, up and down, or both, without changing the shape or orientation. For a positive constant k and a parent function f of x, so if you have f of x plus or minus k, that is a vertical translation. So what's happening there is you're adding or subtracting a constant term from the value of y. Remember, f of x, g of x, h of x, they mean or they are the y values. So if you add or subtract from the y value, you're going to shift the graph up or down, in this case, 3 units. So if you start with f of x equals x squared, that's the parent quadratic function, that's that red graph, and you switch that to y equals x squared minus 3 or g of x or h of x equals x squared minus 3. That's going to shift the parent function, that red graph, down 3 units to make that green graph. So the thing to keep in mind here is whenever you add or subtract from the value of y, f of x, g of x, h of x, they are the value of y. Whenever you add or subtract, that's going to shift the graph up or down. In this case, we went from f of x equals x squared to y equals x squared minus 3. It's going to shift the graph down 3 units. So when you add to the value of y, it shifts the graph up. When you subtract from the value of y, it shifts the graph down. Once again, for a positive constant h and a parent function f of x, so h is the constant. If you go to f of x plus or minus h, that is a horizontal translation. It's going to shift the graph left or right. So let's say we start with f of x equals x squared, the same parent quadratic function we had over there. F of x equals x squared, that's the red graph. If we switch that to y equals x minus 2 squared, notice the graph is shifted to the right 2 units. So when you subtract from the value of x, that's going to shift the graph to the right. In this case, we're subtracting 2 from the value of x. So we went from x squared to x minus 2 squared, and that shifts the graph to the right 2 units. So what to keep in mind here? On horizontal translations, when you add to the value of x, it's going to shift the graph to the left. When you subtract from the value of x, as is this, it's going to shift the graph to the right. On vertical translations, when you add to the value of y, it shifts the graph up. When you subtract from the value of y, it shifts the graph down. So on horizontal translations, it's opposite of how you're trained to think. Normally when you think add, you go to the right. Or when you think subtract, you go to the left. Well, it's the opposite of that. When you subtract from the value of x, it's going to shift the graph to the right. When you add to the value of x, that's going to shift the graph to the left. So vertical translations, adding or subtracting from the value of y shifts the graph up or down. Horizontal translations, adding or subtracting from the value of x, shifts the graph to the right or left. When you add to the value of x, shifts the graph to the left. When you subtract from the value of x, shifts the graph to the right. How are the functions y equals x and y equals x minus 2 related? And how are the graphs related? Well, if you look at the coordinate chart, if you put values in for x into y equals x, so if you put negative 2 in for x, y is going to be negative 2. If you put negative 1 in for x, y is going to be negative 1. So these are the x values, these are the y values. But if we change that to y equals x minus 2, if you substitute negative 2 in for x, y is negative 4. Negative 1 in for x, y is negative 3. And so on. Now look at the differences in the y coordinates. From y equals x to y equals x minus 2, you can see it's subtracting 2 units. So when you go from y equals x to y equals x minus 2, you're subtracting 2 from the value of y. Think about what that does to the graph. If you subtract 2 from the value of y, it's going to shift the graph to the down 2 units. So each output for y equals x minus 2 is 2 less than the corresponding output for y equals x. Notice again on the graph, from y equals x, the red graph, to y equals x minus 2, the blue graph, you can see it's shifted down 2 units. But there's actually another translation taking place. You're subtracting 2 from the value of y, it shifts the graph down 2 units, but in this case, in this particular one, you're also subtracting 2 from the value of x, and you can see what that does, that shifts the graph to the right 2 units. So there's really 2 translations taking place at once here. You're shifting down 2 units because you're subtracting 2 from the value of y. The value of y is that whole right side. Y equals x. In this case, x is actually the value of y. So when you subtract 2 from the value of y, it shifts the graph down 2 units. But also you're subtracting 2 from the value of x, and as I said in the previous slide, it's going to shift the graph to the right, in this case 2 units. When you subtract from the value of x, it shifts the graph to the right. When you subtract from the value of y, both of those are taking place here, and it shifts the graph down. So the graph of y equals x minus 2 is the graph of y equals x translated down 2 units, but you could also say translated to the right 2 units. What is the graph of y equals x squared minus 1 translated up 5 units? Well, if you're going to translate that or shift that up 5 units, you're going to add 5 onto the value of y. You take any point and you add 5 onto the y value, it's going to shift that point up 5 units. That's what's going to happen here is every y value on the graph of this y equals x squared minus 1, every y value you're going to add 5 onto it, it's going to shift the graph up 5 units. So what we're looking at here is the red graph, y equals x squared minus 1. Imagine taking every y coordinate on that red graph and adding 5 to it. It's going to shift the graph up 5 units, and it's going to become that blue graph. So if we go back to the equation, if you add 5 onto the value of y, the value of y is the whole right side. It says y equals x squared minus 1. So x squared minus 1 really is y. If you add 5 onto that, so if you take x squared minus 1 and add 5 onto it, you're going to get x squared plus 4. So when you go from y equals x squared minus 1 to y equals x squared plus 4, you can see the graph is shifted up 5 units. Just to check that, if you look at this point right here, 0, negative 1, if you add 5 onto the value of y, it's going to make that 0, 4. Or if you take this point here at 1, 0, if you add 5 onto the value of y, it's going to make that 1, 5. So every y coordinate, you're adding 5 onto it to shift the graph up 5 units. So the graph of y equals x squared minus 1, that's the red parabola, is translated up 5 units to get the graph of y equals x squared plus 4. If you look at the coordinate chart on this, if you put negative 2, negative 1, 0, 1, and 2 in for x into y equals x squared minus 1, it's going to be, for the y value, it's going to be 3, 0, negative 1, 0, and 3. If you put those into y equals x squared plus 4, the y values become 8, 5, 4, 5, and 8. You can see the difference in the y values. From the red graph to the blue graph, the y values are moved up 5 units, or you're adding 5 onto the value of y. So every value in the y equals x squared plus 4 output is 5 greater than the value in the y equals x squared plus 1 output. The graph is shifted up 5 units. How are the functions y equals 2x and y equals 2x minus 3 related? And how are their graphs related? Well, if you look at the coordinate chart for y equals 2x and y equals 2x minus 3, if you put negative 1, 0, and 1 in for x into both of these equations, y equals 2x and y equals 2x minus 3, for y equals 2x, the y values are negative 2, 0, and 2. So if you put negative 1 in for x, it's negative 2. Put 0 in for x, it's 0. Put 1 in for x, it's 2. Likewise, if you put negative 1 in for x into y equals 2x minus 3, you get negative 5. 0 in, you get negative 3. And 1 in, you get negative 1. So if you look at the y values, difference in the y values from y equals 2x to y equals 2x minus 3, you can see the y values are shifted down 3 units. From y being negative 2 to y being negative 5, 0 to negative 3, and 2 to negative 1. Each of those y values is shifted down 3 units. So you can imagine what's going to happen to the graph. without even seeing the graph. If the y values are each shifted down 3 units and the x values aren't changing, the graph will be shifted down 3 units. So each output for y equals 2x minus 3 is 3 less than the corresponding output for y equals 2x. And you can see that on the graph. The graph of y equals 2x is this purple line, and the graph of y equals 2x minus 3 is the green line. You can see from the purple line to the green line, it is shifted down 3 units. Now don't get confused here. That's not a subtraction from the value of x. If you're going to subtract 3 from the value of x on y equals 2x, you would put the x in parentheses. So it would be y equals 2 times the quantity x minus 3, which would end up being y equals 2x minus 6. So know the difference between subtracting 3 from the value of y, as is the case here, and subtracting 3 from the value of x. This is subtracting 3 from the value of y. The value of y is that 2x. If you subtract 3 from it, it's just y equals 2x minus 3. But if you were to subtract 3 from the value of x, you would put the x in parentheses, so it'd be 2 times the quantity x minus 3. But in this case, you can see the graph is shifted down 3 units. You can see that in the coordinate chart with the y coordinates, and you can see that in the graph. It's shifted down 3 units. A reflection flips the graph of a function across a line such as the x-axis or the y-axis. Each point on the graph of the reflected function is the same distance from the line of reflection as its corresponding point on the graph of the original function. So if we start with this black graph, this f of x, you have points of 3, 4, 1, 1, and 6, 1. Notice what happens when you reflect over the y-axis. Now, making a reflection, you've all seen pictures of lakes with trees on the shoreline reflected into the lake. That shoreline, imagine this y-axis is the shoreline. You have the trees on the lake reflected over the shoreline and into the lake. That's kind of what you're seeing here. So for these points 1, 1, 3, 4, 6, 1, when those are reflected over the y-axis, notice what happens, what changes. That's what you need to keep in mind, is what changes when you reflect over the y-axis. When we go from 3, 4 to negative 3, 4, we go from 1, 1 to negative 1, 1, we go from 6, 1 to negative 6, 1. So what's changing? When you make a reflection over the y-axis, the x value changes from positive to negative or negative to positive, depending on which way you're reflecting. So from black to red, you can see the x value is changing from positive to negative. But if you go from red to black, notice the x value is changing from negative to positive. So when you reflect or make a reflection over the y-axis, the value of x is what changes. Changes from positive to negative or negative to positive. The y values stay the same. Now look what happens when you reflect over the x-axis. So if you go from black to green, the black graph to the green graph, notice the points. You go from 3, 4 to 3, negative 4, go from 1, 1 to 1, negative 1, and go from 6, 1 to 6, negative 1. So when you make a reflection over the x-axis, the value of y changes. So when you reflect over the x-axis, the value of y changes from positive to negative or negative to positive, depending on which way you're reflecting. Once again, reflect over the y-axis, the value of x changes signs. Reflect over the x-axis, the value of y changes signs. Let g of x be the reflection of f of x equals 3x plus 3 in the y-axis. What that means is you're reflecting over the y-axis. What is the function rule for g of x? So we're going to start with this f of x equals 3x plus 3. That's this blue graph. And you're going to reflect that over the y-axis. When you reflect a graph in the y-axis or over the y-axis, remember the x values change signs. They go from positive to negative or negative to positive. The y values on those points will stay the same. So for f of x equals 3x plus 3, if we're going to reflect that over the y-axis, the only thing that changes is the value of x. It changes signs. So that x is now going to become negative x. So you might write this as going from f of x to f of negative x. The x value changes from positive to negative or negative to positive. In this case, it's positive, so it's becoming a negative x. So now we have 3 times negative x plus 3. That would end up being negative 3x plus 3. So when you make that reflection over the y-axis, g of x, the new function, g of x equals negative 3x plus 3. So if we graph that from f of x equals 3x plus 3, that was our starting function, the blue function, the blue graph. When you reflect that over the y-axis, all of these x values went from positive to negative, or down here from negative to positive. The only one that doesn't change is this 0, 3, because that is the y-intercept. And the x value, with it being 0, is not going to change signs. So once again, from blue to red, the x values change from positive to negative, or down here from negative to positive. When you make a reflection over the y-axis, the x value changes signs. So if you had f of x equals 3x plus 3, it's now g of x equals negative 3x plus 3. Let h of x be the reflection of f of x equals 3x plus 3 in the x-axis. That means you're going to take this f of x equals 3x plus 3 and reflect it over the x-axis. What is the function rule for h of x? So we're going to change this f of x into h of x, and the h of x will show the reflection over the x-axis. So here's your f of x equals 3x plus 3. It's a blue graph. You can see the y-intercept is 3, the slope is 3. That is the graph of f of x equals 3x plus 3. You might think of that as y equals 3x plus 3. Remember, when you make a reflection across the x-axis or over the x-axis, the value of y changes. The sign of y changes. So we're going to start with f of x equals 3x plus 3. F of x, that's your y value, that's equal to this 3x plus 3. So this whole right side is the value of y. If we're going to reflect that over the x-axis, we're going to change the sign of the value of y. So we're going to take the negative of f of x equals 3x plus 3. We're taking the negative of that whole right side. So the negative of that whole right side is the negative of 3x plus 3, which would turn out to be negative 3x minus 3. So we're taking the negative of the y value. The y value is the whole right side. If you take the negative of the entire right side, it's negative 3x minus 3. So h of x, the new function, would be h of x equals negative 3x minus 3. So what we're going to see on this graph, it's going to show up here, is all these points on this blue graph are going to be reflected over the x-axis. So every value of y is going to change from positive to negative or from negative to positive. The only value of y that will not change is this value of y at 0. At that point, negative 1, 0. That point will stay right there. And you can see it does. Point negative 1, 0 stays as it is. But every other point from blue to red, the value of y changes from positive to negative or from negative to positive. So when you make a reflection over the x-axis, you're changing the value of y, or changing the sign of y. When you make a reflection over the y-axis, you're changing the value of x, or changing the sign on the x. A vertical stretch multiplies all y values of a function by the same factor greater than 1. So what a vertical stretch will do to a graph is it's going to stretch it away from the x-axis. So when you multiply, you think of a point. If you multiply the y value by a number greater than 1, it's going to stretch it away from the x-axis. Let's say you had a y value of 3, and multiplied it by 2, it's going to become 6. Or if you had a y value of negative 3 multiplied by 2, it's going to be negative 6. So it's going to stretch away from the x-axis. A vertical compression, some teachers refer to it as shrink, reduces all y values of a function by the same factor between 0 and 1. So let's say you had a y value of 4. You multiplied that by something between 0 and 1, say 1/2. If you went from 4 and you multiplied by 1/2, that's going to become 2. It's going to compress down towards the x-axis. Or let's say you had a y value of negative 4 and you multiplied it by 1/2. from negative 4 multiplied by 1/2, it's going to become negative 2. So it's going to compress toward the x-axis. For a function f of x and a constant a, y equals a times f of x. So what this means is that we're multiplying the y value by a constant term. It's going to be a vertical stretch when that constant term is greater than 1. So if you multiply the y value by something greater than 1, it's going to stretch away from the x-axis. It's a vertical compression when that constant term is between 0 and 1, such as what I mentioned with 1/2. If you multiply the y value by a number between 0 and 1, it's going to compress the graph toward the x-axis. If we look at some coordinate charts here, from f of x equals x plus 2 to 3 times f of x, which would equal 3x plus 6. We're going from x plus 2 to 3x plus 6. We're multiplying the y value by 3. You can see in f of x equals x plus 2 on that coordinate chart versus 3x plus 6, you can see the y values are multiplied by 3. So what would happen with that graph is it would stretch away from the x-axis by a factor of 3. Or if we look at f of x equals x plus 2 and we make that 1/3 times f of x equals 1/3 x plus 2/3. So we're multiplying the y value by 1/3. Look at the y values. They go from 1 to 1/3, from 2 to 2/3, and from 3 to 1. So imagine that on the graph. If you had y values go from 1 down to 1/3, from 2 down to 2/3, and from 3 down to 1 on a graph, that would compress toward the x-axis. So when you multiply, if you take an equation or a function, you multiply the y value by a number greater than 1, graphically that's going to stretch away from the x-axis. If you multiply the y value by a number between 0 and 1, that's going to compress toward the x-axis. So here we have 3 graphs. The parent function is y equals x. That's the parent linear function. These other functions originate from that parent linear function y equals x. Now you can see what's happening here. We're multiplying from red to green. We're multiplying the y value by 3. And from red to blue, we're multiplying the y value by 1/2. A vertical stretch pulls away from the x-axis, or stretches away from the x-axis. A vertical compression pushes toward the x-axis, or compresses toward the x-axis. Notice how the parent function y equals x is stretched. So from red to green. This graph is stretched away from the x-axis because we're multiplying the y value, the whole right side, by 3. So what was 1/1 now becomes 1/3. And what was -1, multiply the y value by 3, now becomes -1, -3. So that red to green, you can see it's stretched away from the x-axis because you're multiplying the y value by a number that's greater than 1. From red to blue, we're multiplying the y value, that whole right side, in other words the x, we're multiplying that by a number between 0 and 1, or 1/2. So from red to blue, you can see from red to blue, the graph is compressed toward the x-axis on both sides. It's tilted toward the x-axis. So what was a point of 1/1 now becomes 1/1/2 because you're multiplying the y value by 1/2. Or what was -1 on the red graph now becomes -1, -1/2 on the blue graph because you're multiplying the y value by 1/2. So it's a stretch when you're multiplying the y value by a number greater than 1. It's a compression when you're multiplying the y value by a number between 0 and 1. Now a number between 0 and 1, an easy way to spot that is it's either going to be a fraction or a decimal, but it's not greater than 1. So don't get confused on the fractions. If you have 3 halves, let's say you multiply the y value by 3 halves, that's greater than 1. That's actually a stretch. So make sure that fraction is not an improper fraction. Make sure you're multiplying the y value still by a number that's between 0 and 1 in order to create a compression. So again, 3/2 or let's say 5/4, those numbers are greater than 1. Those would be stretches. So don't just say every time you see a fraction it's going to be a compression, because if it's an improper fraction, that would be a stretch. The graph of g of x is the graph of f of x equals 4x compressed vertically by the factor 1/2 and then reflected in the y-axis. What is the function rule for g of x? So we're going to take that f of x, we're going to change it into g of x. We're taking that f of x equals 4x, we're going to do two things to it. We're going to compress it by a factor of 1/2 and also reflect it in the y-axis. So f of x equals 4x is what we're starting with. If we compress that by 1/2, remember when you make a compression, you have to multiply the y value by a number between 0 and 1, in this case 1/2. So we're multiplying the y value, which is that whole right side, that 4x, we're multiplying that by 1/2. That becomes 2x. But we're not done, because we still have to reflect it in the y-axis. So we're looking at g of x equals 2x, but we're not quite to g of x yet. We need to make a reflection in the y-axis or over the y-axis, so we have to take the negative of the value of x. When you make a reflection over the y-axis, the value of x changes from negative to positive or positive to negative on those points. So if we take the negative of x, that creates a reflection over the y-axis, it becomes negative 2x. So our new function rule, our g of x, is g of x equals negative 2x. We did two things. We compressed it by 1/2. So we started with 4x, we compressed that by 1/2, it became 2x. And then we reflected that over the y-axis. When you reflect over the y-axis, you take the negative of x. That became negative 2x. So g of x equals negative 2x is the new function rule. What transformations change the graph of f of x to the graph of g of x? So we're going from f of x equals 2x squared to g of x equals 6x squared minus 1. So you have to think, what transformations took place? Did you shift left, right, up, down? Did you stretch? Did you compress? Did you reflect over the x-axis? Did you reflect over the y-axis? All of those things could have taken place. So if we go from f of x equals 2x squared to g of x equals 6x squared minus 1, think about how you went from 2x squared to 6x squared. How would you go from 2x squared to 6x squared? You'd have to multiply by 3. So we multiplied the y value, that whole right side, by 3. And remember what that does. If you take a point, you multiply the y value by 3, that stretches the graph away from the x-axis. So there was a stretch taking place there by a factor of 3. Then we also subtracted 1. So we multiplied 2x squared by 3 to get 6x squared and subtracted 1 from it. Remember what that subtracting 1 does. When you subtract 1 from the value of y is that whole right side. When you subtract 1 from the value of y, you take a point, you subtract 1 from the y value, it's going to shift the graph of that point down 1 unit. So we multiplied the y value by 3, we subtracted 1 from it. Multiplying the y value by 3, that's going to be a stretch vertically by a factor of 3. So the graph is stretched away from the x-axis by a factor of 3. And then the subtraction of 1 from the value of y, if you subtract 1, it's going to translate or shift the graph down 1 unit. So those two things took place. Stretched by a factor of 3 and shifted down 1 unit. The graph of g of x is the graph of f of x equals x stretched vertically by a factor of 2 and then translated down 3 units. What is the function rule for g of x? So we're going to take this f of x equals x, that's the parent linear function. That would go through the points 1, 1, 0, 0, -1, -1. That line. We're going to do two things to it. We're going to stretch it by a factor of 2. That means stretch away from the x-axis by a factor of 2. And we're going to also translate or shift it down 3 units. So starting with f of x equals x, to stretch that by a factor of 2. When you make a stretch by a factor of 2, you're multiplying the y value by 2. Remember, the y value is the whole right side. So in other words, x here. If you multiply that by 2, it becomes 2x. Now we also need to shift that or translate that down 3 units. So take that 2x, remember that's the y value right now. If we shift that down 3 units, we're going to subtract 3 from the value of y. So if that is the value of y right now, after that stretch, shift that down 3 units, it becomes 2x minus 3. So there it is, g of x equals 2x minus 3. Went from f of x equals x to g of x equals 2x minus 3. We stretched by a factor of 2, and we shifted it down 3 units. The graph of g of x is the graph of f of x equals x, stretched vertically by a factor of 2 and then translated down 3 units. What is the function rule for g of x? So we're going to take this f of x equals x, which happens to be the parent linear function, and we're going to do two things to it. We're going to stretch by a factor of 2 and then translate down 3 units. So starting with f of x equals x, if you want to stretch that by a factor of 2, you're going to multiply the y value by 2. The y value is this whole right side, because f of x equals x. So we're going to multiply that x by 2. We now have f of x equals 2x. But we also need to shift that or translate that down 3 units. Remember, if you take a point on any graph and you want to shift it down 3 units, you would subtract 3 from the value of y. Right now, the value of y is 2x. If you subtract 3 from that, it becomes 2x minus 3. So there it is. G of x equals 2x minus 3. That's taking this f of x, stretching by a factor of 2, and then shifting it down 3 units. What transformations change the graph of f of x equals x squared to the graph of g of x equals x plus 4 squared minus 2? Well, you can see two things taking place there. You're adding 4 to the value of x, and you're subtracting 2 from the value of y. The value of y is the whole right side. So if you add 4 to the value of x, remember when you add to the value of x, that's opposite of how you're trained to think. Usually when you think add, you're going to the right. But when you add to the value of x, it's actually going to shift the graph to the left, in this case, 4 units. Now it's minus 2, you're subtracting 2 from the value of y. The value of y is the whole right side. So imagine taking a point, you subtract 2 from its y value, it's going to shift down 2 units. So that negative 2 there, that subtracting 2, indicates a shift or a translation down 2 units. So the two transformations that took place are, it translated left 4 units because you added 4 onto the value of x, and it shifted or translated down 2 units because you subtracted 2 from the value of y. Which of the following is the graph of y equals negative 3x minus 6 reflected in the y-axis and vertically compressed by a factor of 1/3? Well, you can take that equation y equals negative 3x minus 6 and perform those two operations on it, reflecting it in the y-axis or over the y-axis, and then compressing it by a factor of 1/3. So y equals negative 3x minus 6. If we are to reflect that over the y-axis, remember what happens when you reflect over the y-axis. The value of x changes signs. So take that x and change the signs. It's now negative 3 times negative x, which would end up being 3x minus 6. But we're not done yet. We still have to compress this by a factor of 1/3. Remember, to make a compression, you multiply the y value by a number between 0 and 1. So we're going to multiply the y value, that's this whole right side, the 3x and the negative 6 together. We're going to multiply that by 1/3. So we're multiplying the entire right side by 1/3, or 3x minus 6 times 1/3, distributed property there. It's y equals x minus 2. So now all you have to do is match one of these graphs up with this y equals x minus 2. So if we break that down, the slope on that is 1, and the y-intercept is negative 2. So you're looking for the graph with a y-intercept of negative 2 and a slope of 1, where you go up 1 and to the right 1. Obviously, it's letter D. The graph of y equals x plus 4 is translated 3 units down. Which point is on the new graph? Well, we can take that equation, y equals x plus 4, see what the new equation would be when you shift that down 3 units, and then decide which of these points lies on the graph of that new equation. So if you take that equation, y equals x plus 4, if you're to shift that down 3 units, remember, when you make a shift down 3 units, you're subtracting 3 from the value of y. So the value of y here is this whole right side. X plus 4 is really the value of y. If you subtract 3 from that x plus 4, you get x plus 1. So y equals x plus 1, that's the new equation. That is this original equation shifted down 3 units. So what we need to do now is decide which of these points, when substituted in, when you substitute the x, y values in, which point makes a true statement when you substitute in. So if you take that point, negative 1, 0, you substitute negative 1 in for x and 0 in for y, you're going to have 0 equals negative 1 plus 1. That's going to make a true statement. 0 equals 0. So that's a true statement. That means that point, negative 1, 0, lies on the graph of this equation, y equals x plus 1. And this equation is this equation, y equals x plus 4, shifted down 3 units. So negative 1, 0 is the point we're looking for, letter I. Graph of y equals f of x is reflected in the x-axis and translated 3 units right, which is the equation of the new graph. So we're doing two things here. We're taking this y equals f of x and reflecting in the x-axis and then also shifting to the right 3 units. So to translate in the x-axis, which means translate over the x-axis, you change the value of y. You change the sign on the y. The value of y is this whole right side. So if we change the sign on the value of y, that's changing the sign on the whole right side. So now y equals the negative of f of x. But we also need to shift that 3 units to the right. When you make a shift 3 units to the right, remember that's opposite of how you're trained to think. Usually when you think go to the right, you think add. But when you shift to the right, you're subtracting 3, in this case, from the value of x. So when you subtract from the value of x, that shifts the graph to the right. When you add to the value of x, it shifts the graph to the left. So in this case, shifting to the right, so it's going to be x minus 3. And we're subtracting 3 specifically from the value of x. So inside the parentheses there is where you put the negative 3. So y equals the negative of f of x minus 3. Negative sign indicates a reflection over the x-axis, and the minus 3 indicates a shift to the right 3 units. Letter C. Which equation represents the vertical translation of y equals f of x up 5 units? When you make a vertical translation up 5 units, you're going to add 5 onto the value of y. So if you add 5 onto the value of y is the whole right side. So y equals f of x, you're going to add 5 onto that f of x. So if you add 5 onto f of x, not too hard, it's going to be y equals f of x plus 5. Letter H. One person wrote the transformations shown to describe how to change the graph of f of x equals x squared to the graph of g of x equals 2 times the quantity x plus 1 squared minus 3. Explain the error and give the correct transformations. So somebody took f of x equals x squared, g of x equals 2 times x plus 1 squared minus 3 and said these were the transformations. Shifted vertically 1 unit up, shifted horizontally 2 units to the right, and shifted vertically 3 units down. And obviously, he thinks there's a mistake. If we go from f of x equals x squared to g of x equals 2 times the quantity x plus 1 squared minus 3, when you add 1 to the value of x, so you take this value of x, you add 1 to it, it's going to shift the graph to the left 1 unit. When you add to the value of x, shifts the graph to the left. Now there's 2 out front. So we're multiplying the value of y, that's the whole right side, by 2. When you multiply the value of y by a number greater than 1, it's going to stretch the graph away from the x-axis by that factor. So we're stretching by a factor of 2. When you multiply the y value by 2, it's going to stretch the graph by a factor of 2. And then minus 3 on the end, when you subtract 3, now we're subtracting 3 from the value of y, so we're subtracting 3 from the whole right side, that's going to shift the graph down 3 units. That one's actually right. So shifting vertically 1 unit up, that should be shifting 1 unit to the left. So they thought adding 1 to the value of x shifted it up 1 unit. It's actually shifting to the left 1 unit. And shifting horizontally 2 units to the right, that should be stretched by a factor of 2. So those are the mistakes, and those are the corrections. Which equation represents the horizontal translation of y equals 3x minus 2 to the left 2/3 units? When you make a horizontal translation to the left 2/3 units, you're going to add 2/3 on to the value of x. When you want to move to the left, you add to the value of x. So take that y equals 3x minus 2, and we're going to add 2/3 on strictly to the value of x. So it's now y equals 3 times x plus 2/3 minus 2. So we're adding 2/3 specifically on to the value of x. That adding 2/3 onto the value of x, that will create a shift to the left 2/3 units. Now you have to match that equation with one of these. So take out the parentheses by using distributive property. Take 3 times x, that is 3x, and 3 times 2/3, that is 2. So y equals 3x plus 2, still minus 2. Don't forget that. Combine the like terms. 2 and negative 2, if you combine those, that would be y equals 3x. And that is letter A. Just a summary of transformations of functions that we've talked about. Vertical translations, that's shifting up or down. When you add to the value of y, that's the whole right side. When you add to the value of y, it's going to shift the graph up. When you subtract from the value of y, it's going to shift the graph down. Remember, the value of y is the whole right side. If you subtract k from the value of y, it shifts the graph down k units. If you add k to the value of y, it's going to shift the graph up k units. Horizontal translations, left and right. This is the one that's opposite of how people are trained to think. Usually when they think add, you go to the right. Usually when they think subtract, you go to the left. This is opposite of that. When you subtract from the value of x, so say you're subtracting h from the value of x, that's going to shift the graph to the right, h units. So when you subtract from the value of x, you're going to shift to the right. When you add to the value of x, it's going to shift the graph to the left. So if you add h onto the value of x, it's going to shift the graph to the left, h units. Again, that is one to remember. When you subtract from the value of x, shifts the graph to the right. When you add to the value of x, that shifts the graph to the left. That one's tough to remember. It's opposite of how you usually think. Vertical stretches and compression. Stretching or compressing, stretching away from the x-axis or compressing toward the x-axis. A vertical stretch is when you multiply the y value by a number that's greater than 1. A vertical compression, on the other hand, is when you multiply the y value by a number that's between 0 and 1. In other words, a fraction or a decimal, where the fraction is not an improper fraction. If you have an improper fraction, that's going to be greater than 1. Make sure the decimal is between 0 and 1. So vertical compression is when you're multiplying by a number that's multiplying the y value by a number that's between 0 and 1. And finally, reflections. When you reflect in the x-axis, or in other words, reflect over the x-axis, you take the negative of y. When you reflect over the y-axis, you take the negative of x. So if you want to make a reflection over the x-axis, take the negative of the y value. If you want to make a reflection over the y-axis, you take the negative of the x value.